groups on the periodic table, because it has to do with our abbreviation. So on the periodic table, you have probably already noticed that there are rows on the periodic table. Now we do not call these rows, we call these in chemistry periods. And then the columns on the periodic table are called groups. The groups are also referred to as families a lot of times because they share very similar chemical and physical characteristics. On this slide, I believe in your notes, you're writing down what these different groups are on the periodic table. So you're labeling just like I have up here. But one thing I do want to point out is that you'll see this staircase with the semi-metals. So if you look up here, you have your semi-metals and metalloids, and then this staircase here is what I'm trying to point out. Everything to the left of this staircase is a metal, and everything to the right is a non-metal. Now, I do want to point out too that hydrogen, which is over here, is a non-metal as well. It's normally classified as a non-metal. So a good question on a test would be, what are majority of the elements on the periodic table? And you would tell me that they are metals because there are so many on this side. Now, one we're going to focus on today are these noble gases right here. So the noble gases I always refer to as the VIP group of the periodic table. This is because they have all of their electrons, every energy level is completely filled. And so all the other metals want to be, or all the other elements over here want to gain and lose electrons or share electrons so that they look like these noble gases here. Sorry. All right. So the valence electrons that are in an atom are the electrons that are in the outermost energy level. So if we were talking like we did yesterday, where we have, our inside of our atom here, and then these energy levels of electrons. If there was only, let's say this is lithium, and so we had 3 electrons there. The valence electron would be this outermost energy, the one that's in the outermost energy level. So not these inner core electrons. These are the ones that are associated most with an atom's ability to, like its chemical behavior. And so these types of electrons are what we spend most of our time talking about. So elements that are noble gases are special because those outermost energy levels are completely filled. Again, if I went back and talked to lithium, the reason why lithium is very reactive is because it could still fill this outer ring here with 7 more electrons. So it is incredibly reactive because it just wants to either get rid of this electron or do something so it's more stable and looks more like one of these noble gases here. So again, noble gases are really special because their outermost energy level is completely filled. They don't really react with anything because of this. And so because their outermost energy level is filled, we can use these noble gases as a way to abbreviate our electron configurations, and we call these noble gas notations. So what a noble gas notation is we put the noble gas that comes, if I was asking to do an electron configuration for a particular element, we would look at that element on the periodic table, and we would find the noble gas that comes before it. We put that noble gas in brackets, and then that implies all of the inner electrons that are in that atom. And then the remainder of the configuration is everything after that noble gas until we get to the element in question. So I'm going to do these examples with you. So we have bromine first. So the first thing that we should always do is find the element on the periodic table. So if I'm looking here at bromine, bromine is this guy here. It's in that 4P's last thing it has. So we always want to, in order to write a noble gas notation, find the noble gas that occurs before it. So we go up a row and then all the way to the right. And then that is going to be the noble gas that comes before it. So we're going to put this noble gas, argon, in configuration, or excuse me, in brackets. So I do that by putting, again, argon in brackets. Now what that does, what I'm implying there, but without having to write it, is argon's configuration. So by just writing that, what I'm telling the person is I've already accounted for all of these inner core electrons. So all of that, without having to write it, is this guy. But since it's an abbreviation, you don't have to write it. So what we do then is we just pick up after this 3p6. We pick up after argon, and that's going to be what we put in the remainder of the configuration. So I'm going to go ahead and erase this part of it. All right. So again, the remainder of this is from argon to, so if I go here, argon is right here. The next thing in the configuration, I go down the row, is going to be 4s2. Then I'm going to go to 3d10. And then 4p, and I count over to bromine, so 4p5. So again, I'm going to start off by writing 4s2. The next thing in my configuration after 4s2 is 3d10. I then finish that and go over to bromine's area of the periodic table, so 4p5 is the last thing in my configuration. And that's it. So again, what we're going to do, just to recap, we have the noble gas that comes before the element. So again, the noble gas here goes in brackets. It's whatever noble gas comes right before the element. And then after that, we just include everything in the configuration after that noble gas to the element's actual box on the periodic table. So for the next example, if we look at barium, barium is here on the periodic table. Now it has a ton of electrons, so if we were to do this normally, it would take us a good minute to write out this entire configuration. But with the noble gas notation, it makes it very simple. So just like we did before, the first thing in our configuration, we need to find the noble gas. So we're going to go up all the way to the right. And that noble gas that goes in brackets is xenon. So I'm going to put xenon in brackets. Again, what that's done is I've now accounted for everything before this on the periodic table. So I've already included all of this on the periodic table until xenon. So the next thing in my configuration is after xenon. I just go find whatever comes right after it. So 6s, and then since barium's right here, just count over. So the last thing in my configuration is just going to be 6s2. And that's it. So it saved us a ton of time doing this noble gas notation. And then our last example is iron. So iron is right here on the periodic table. Iron's abbreviation is Fe. Again, you always have to find the noble gas that occurs before it. So we go up all the way to the right. And we're going to use argon in brackets. That's the noble gas. Put argon in brackets. Oops, I'm sorry. So the next thing in my configuration is whatever comes after argon. So I go all the way back down here, and the next thing is going to be 4s2. And then after 4s2, this is where iron is, so it's going to be 3d is next. And I count over 1, 2, 3, 4, 5, 6. And that is iron's noble gas notation. So a couple important things about noble gas notations. It always has to be a noble gas in brackets. So this here can only be a noble gas, which means it has to come from this group here. The other thing is a noble gas cannot be its own configuration. So if I had asked for, let's say, the noble gas of xenon, for example, right here, I cannot just put xenon in brackets and call it a day. I'd have to go to the noble gas before it, which is krypton, and put that one in brackets, and then finish out the rest of the configuration. So it's an important thing to know. All right. The last thing we need to talk about in regards to valence electrons is how we can represent them, like an easy way to represent how many valence electrons an element has. And so these valence electrons, again, are really important because they determine chemical behaviors for the element. So we use something called an electron dot structure to do this. In this electron dot structure, the inner core electrons and the nucleus are represented by the element symbol, and then we're going to put dots around the nucleus or around that symbol to represent the valence electrons. So here, the way we determine how many valence electrons there are on a periodic table is by the group number. Now, I'm going to kind of go back, so I believe you're probably going to have to turn your paper back over, but if we revisit our periodic table that I had over here. Our valence electrons can be shown, again, by our group numbers. So I'm going to write them up top for you. Let's use a different color, choose like a red. So in this group 1 here, since it's group 1, we're only going to have one valence electron. That means everything in this group only has one valence electron. Group 2, everything has 2 valence electrons. Again, a group means a column, so that all has 2. We are going to skip this middle group. These are called transitional metals, and I will never ask you for this. If I'm telling you to skip it, we're not going to go over this. So we're not worried about how many these are. Then you have over here, it's going to be 3. So I know if you're looking at the group number, it honestly says 13 up there. But what we do is we take the 1 away in front. So if I just kind of ignore the 1, it is 3. So this entire group has 3. Also, this is why if you look at some periodic tables, it'll say 3A. And the A there is to imply it's not the actual group number, but it's telling you how many valence electrons there are. Carbon's group will have 4. Nitrogen's group has 5. Oxygen's group has 6. Fluorine's group has 7. And then our noble gases have 8. Again, so what this means is everything here has 8 valence electrons. These are our noble gases. Now, I will say, we normally say everything has 8, but honestly, that's only for these guys down here. And the reason why is because helium here, helium only has 2 valence electrons. So there's no way, it only has 2 electrons total. So there's no way it can have 8. So this here, again, has 2 valence electrons because it only has 2. But it has, everything else has 8. All right, so let's go back to our electron dot structures. So when we do this, we need to first, if I'm doing this for an element of phosphorus, I'm going to look for phosphorus on the periodic table. Phosphorus is in the group that has 5 valence electrons. It's not nitrogen's group. So the way that we do this is we are going to imagine that there is a box around it. This box does not really exist though, okay? And the way that we do these is we're going to place those 5 valence electrons, one on each side of the box. So I'm going to place 1, 2, 3, 4, 5. And so we place one on each side, and then I come back and start pairing them up. You should not have like 2, 2, and 1 here and leaving this side blank. You want to always do, so again, you couldn't see what I was saying, but 2, 2, and 1 with this side being blank because it's just not following how we do that. All right, so if we look here at our examples, we have bromine first. Bromine is in fluorine's group, so that means it has 7 valence electrons. If I follow, I'm going to imagine that there's a box around it, so I'm going to say 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. And you'll hear me too say either Lewis dot structures or electron dot structures, and they're the same thing. I just interchange them. The example that is neon. So neon's our noble gas. It has 8 valence electrons. So I have 1, 2, 3, 4, 5, 6, 7, 8. So that's my noble gas configuration for that one. Sulfur has 6 valence electrons, so I'll start off at the top. 1, 2, 3, 4, 5, 6. Those 6 valence electrons there. And then calcium will have 2, and so I've got just 1, 2. Now for calcium, honestly, it doesn't matter which side that they're on. Like this would be acceptable here. This is acceptable. What is not acceptable is 2 on the same side. So this would be incorrect. Also make sure that we put the electrons, so like for sulfur, notice that I never put them going out like this. They have to stay on the sides of the box. So this is also incorrect. We don't do it this way. So after this, hopefully you're able to do the practice that I've assigned, and I hope you all have a good day. Let me know if you have any questions. But yeah, have a great day, and I will talk to you guys later. Bye.